while I'm here. Okay, so Lenz law. Now Lenz law. Wait, my screen is still visible, right? Just clarify. You guys can see my screen?
Yeah.
Okay. Now Lenz law is basically what happens when, if let's say I take, it basically states that when you move a magnet for induction, it will induce a current that opposes the thing, the movement. I think it's much better if I just show it to you. So let's do that. So let's say I take a north-south magnet and I bring it towards a coil. Let's say I'll just represent this coil with a circle because that's just much easier. If I bring the magnet towards the coil, like so, we know that our magnetic field for a magnet is quite clear. It's like N and S. But the question is, in what direction will your current be generated clockwise, like so, or will it be anti-clockwise? And that's what Lenz law is really talking about. How will your current be generated? So when we're looking at that kind of stuff, what you have to know is that the current induced will always oppose the movement of the magnet. So an example of this is, let's say we bring the magnet towards the coil, like so. If we bring it towards it, then it's okay. We have a magnetic field that's opposing. That means that if I were to show you if I were to ask you what the polarity is on this side, do you think it'll be north or south on the left side of the coil? Anyone?
What I was listening.
God damn it.
I'm sorry.
It's okay. It's okay. It's okay. It's okay.
Listening right now, so
Uh,
I just yeah, focus.
Basically, Lenz law states that the induced current induced will oppose the direction of motion. This is the simplest way of it, but there's actually a proper. You know what? I'll just check the proper definition. Give me a moment while I check on it. The proper definition of Lenz law is, where is this thing? Yeah. The induced current in a loop, and you need to remember this, by the way, because sometimes the Dr. Locke will ask. The induced current in a loop is in the direction that creates a magnetic field that opposes the chain magnetic flux through the arrow loop. So an example of this is, so in simpler terms, current induced will oppose the direction of motion because the chain magnetic flux is going towards it. And of course, that means that the induced current will oppose it. So what does that mean in this sense? Then what it means is that if I bring this magnet towards the coil, I'll induce a current in it because the flux will be increasing. So in this case, then the main question remains: when it comes to Lenz law, we're really talking about what direction will the current be induced? Will it go in this direction, or will it go in the direction that's like this, like it's clockwise, or are we looking at anti-clockwise direction like this? So how do we answer this question is quite simple, and it really has to do with the polarity. Now, if I have to move the north pole of a magnet here, and I'll just need current, what do you think will the polarity be on this side, on the left side?
North Pole. Oh, is this like a wire? This is like a wire, right?
Yeah. The coil will be like a wire. I'm just representing it by a circle.
So, what do you mean by the polarity of the wire?
I would say not the polarity, but more what I mean by the polarity of the wire is because we know that there's a magnetic flux, right? And it will change. When a magnetic flux changes, then a current will be induced because EMF is induced. So there will be a current, but we don't know in what direction. But then this current, okay, I think this one needs a bit more foundational. So we know a current, if let's say I have a coil, and let's say I tell you it's going like this. let's say I tell you that the current is going clockwise. Where is the north and south? Sorry, wait. Why did I draw the arrow like that? Where is the north and south poles of this coil? And it's a coil, not just like one loop. Like let's just take a bunch of loops. I'm just simplifying it. Do you get?
North, south.
Yeah, the north and south. Where is the north and where is the south, basically?
I have no idea.
Ah, I see. Okay, that's where. So okay, this one is where I need to. The only way I can
What
show
is
it to you. Hmm?
out of a wire? What do you mean by the north and south of a wire? Like a wire is just
Oh,
something that runs.
okay. Wait, now I need to go. Yeah, I need to go back a bit. So basically, whenever there's a magnetic current, no, sorry, not magnetic current. Whenever there's an electric current, a magnetic field will be induced. As for why, there is an explanation, but I won't go through that. But basically, what you need to know is that whenever there's an electric current, like for example in this coil, there's electric current going through it, there will be a magnetic field induced within by this coil, the induction of a magnetic field. And when it comes to induction of magnetic field, it's like so. I'm going to a PBL to show it because I have a very good like diagram of it. You will follow the right hand thumb rule. Where is it? Propulsion. Ah, there we go. So let's see. Essentially, what happens with coils is that and like the north south there doesn't actually exist normally. There's no magnet or whatever. But because of the way the current flowed through this entire thing, there will be. So basically, your electric current is going from left to right, or not left to right. Sorry, it's going like this because of the way that it works, right? Because the plus is over here. It goes inside and then goes clockwise and clockwise and clockwise and clockwise and clockwise, clockwise, clockwise. Uh,
Yeah.
so if you take your thumb, and I want you to position it in the way that you see in the picture, the diagram, take your hand in front of you, and try to imagine your fingers. Your fingers is the direction of current. That's what your fingers. Your four fingers, not your thumb, is your direction of current. So in this case, because it's like a coil, you can try to like put your thumb in front of you, and I suggest you do that in real life right now. Like just try to do that, and you can kind of see how your fingers will like coil. That'll be your direction of current.
Okay.
And then wherever your thumb is, by the way, this must be on your right hand, never on your left. Wherever your thumb is, that is the magnetic field. So your thumb, if it's going in the right direction right now, like how it should be, your thumb is basically your north side.
Okay.
Mm.
Oh,
So that's basically how it works. And so basically you'll have like a magnetic field induced like so. Magnetic field lines are like this. But yeah, your
oh,
thumb will be your north, and then the back will be south. Hmm?
okay, I got it.
So then the question is, but the problem is if we induce a current, what we're actively doing is the opposite, where we bring a magnetic field here, and then but we don't know whether the current will be clockwise or anti-clockwise. So then, but then by Lenz's law, it says that the induced current will create a magnetic field that opposes the change in magnetic flux. When we oppose the change in magnetic flux, that means that the magnetic field will try to oppose the direction of motion. I think I said too many things at once, but
No, I get it.
so it's going here. So what do you think the pole here is? Just give a guess.
What?
Yeah, it'll be north. That's correct. So north and then south. So, and I think I forward this question to Jauher. If it's north then south, will the will like just looking at it like this in the tree, try to give it a 3D way. Do you think it'll be clockwise or anti-clockwise? This goes to Jauher. Do you think this will be a clockwise current or an anti-clockwise current?
Anti-clockwise?
Yeah, it will be anti-clockwise. So take that thumb again, like what we saw just now. And what you'll notice is here. Where is it? Oh, I can't flip images actually. This is foolish. Well, I mean, I can do this. I guess that works. But yeah, uh, yeah, you will get like an anti-clockwise coil. So you can kind of see how, yeah, you can see it's anti-clockwise because when you put your thumb like that, where because in this case, instead of having the current originally, you have the pulse. So you can put your thumb on the left side, and then you can see, oh, you'll notice your current is like going clockwise, anti-clockwise, sorry. Is going like upwards, like that. So that's why here, the current induced will be like this. It will go upwards, anti-clockwise. Does that make sense?
Yeah.
Hmm. Jaron, does that make sense?
Yeah.
Okay. So I think you guys understand like if it was like a north south, uh, what polarity will the left side be? Oh wait, sorry. So let's say movement. The movement is like this. What polarity
It
will this side be? Hmm.
will be south.
Yeah, it'll be south. And then north. And I think you guys can figure it out from here. Where is it clockwise or anti-clockwise?
Clockwise.
Yeah, clockwise, based on the hand. Now the tricky part is what happens when the magnet is moving away? And there's actually a difference on what happens. So when the magnet moves away,
Won't it just be the opposite?
oh sorry, yeah, it will just be opposite.
Yeah.
So in this case, because we want to oppose the direction of motion, your magnet wants to attract you back. Your coil wants to attract you back. You'll want to bring you back. Honestly, there's like a very easy like analogy I can give for this, but anyway, yeah, you want your coil will
Okay.
want to bring you back basically.
What's the analogy?
Okay, so basically, kind of like how sometimes like when you love someone and that person you love gets closer to you,
That
you want them
oh,
to like you want to push them away at
like
first.
the grass is always greener on the other side.
Yeah, basically. Like when you're love, that's the same way with the magnet. Like when someone you love gets closer to you, then at first you're gonna push them away. But then when they start to leave, you're gonna wish you had them back, basically.
Oh man, that's a really
Yeah, that's basically the best way I can explain it. But yes, that's how Lenz law works.
nice. And I'm assuming the current would be clockwise when it's moving
uh,
away.
yeah, it's clockwise when it's moving away. So yeah, in this case, the direction of motion and the poles are the most important things. And always and keep this in mind in case you have like because right now it's quite simple to see, but sometimes you'll have like cases where it's like the magnetic field might be going inside. So just keep that in mind. Sometimes in this case, it's not easy for me to visualize it for you, but when your current is going inside, you can try putting your thumb in front of you. Not current. Your magnetic field. When your magnetic field is going inside, yeah, when your magnetic field is going inside, yeah, let's say this is B. Sorry, I can't really draw it because it's going in. When your magnetic field is going inwards, so your north is going in, you can try imagining your thumb poking through your screen right now, and then you can kind of see like the coils. So your current will look something like uh, this. Does that make sense to everyone?
Yeah.
Hmm. Jar?
Yeah.
Okay, nice. So yeah, that's basically Lenz law in a nutshell. Yeah, there's that. Lenz law basically I've covered that. Okay, I'll just stop the recording for Lenz law so that people don't need to watch more than they need to.
And the direction of the magnetic field is always from south to north, right? Or yeah, south to north.
The what?
The direction of the magnetic field is always south to north.
Oh, the direction of magnetic field is actually from north to south. The field
Are you
lines,
sure?
you mean? Yeah, I'm certain of it. Uh,
Then previous example,
Mm-hmm.
where like go back
Mm-hmm.
here.
Mm-hmm.
No, forward.
Yeah, yeah.
This.
Mm-hmm.
So in this one, the field lines are going from north to south
Oh, wait. Okay. I think it's a bit hard for me to explain.
because if
Yeah, yeah. I know
one
what you
goes
mean. How do I explain this? Okay, if the magnetic field lines are going like this to this, yes, your end product will be N. Like so.
yeah
Yes, you are
yeah,
correct in saying like this. Yeah, yeah. That is correct. If you're talking about direction
but
magnetic field, I'd be like that.
but
Uh,
then what about the but magnetic field is south to north, right? All every time, or is that
yeah.
uh, incorrect?
The best way I can explain it is that if it's like this, that'll be like south to north. But then, like, if like let's say it's a magnet, that's actually a very good question. It will be like this, and then it'll, like go out, and then it'll be like this. I don't know how to explain it, but yeah, that's. How do I explain that part? Huh, that's a good question. I need to look
So
into that a bit more.
it's okay. It like loops back into itself if it's just a singular magnet. So it
Yeah,
just
yeah,
loops back
obviously.
in. It's like south to north, then it exits from the north and goes back to the south.
Yeah, that's correct.
Ah,
Yeah, yeah. I
okay,
think
okay,
yeah, I think that should be fine then. But yeah, it is from south to north. It will go in the direction of north, basically, to answer your question.
okay, okay.
Hmm. So yeah, okay, I'll close the Lenz law thing. Any other question about Lenz law?
Uh, no, I think I got it.
Hmm.
Yeah.
Okay, Chowron, you?
Say
Okay,
I did
that'll
not.
close the